Okay, so the problem I'm going to be doing right now is a problem where there's a buffer solution of a weak acid and its conjugate base, and you are adding a certain amount of a strong base, NaOH. And the question says, a buffer solution of volume 100 milliliters is 0.1 molar CH3COOH and 0.1 molar NaCH3CO2. And that salt contains the anion of the weak acid. What are the pH and pH change resulting from the addition of 10 milliliters of 0.95 molar NaOH, the strong base, to the buffer solution? So the first thing you do for finding the pH of the original buffer solution is use Henderson-Hasselbalch equation, which is pH equals pKa plus log concentration of base over concentration of acid. So in this problem, you'll have pH equals pKa plus the log, and the base will be the anion of the salt, which is the conjugate base of CH3COOH, so it's just CH3CO2 over the weak acid. So one thing to note here is that there are equal concentrations. They are both 0.1 molar, so eventually it's going to cancel out, but you can just go ahead and plug it in. And also, you'll get the value from a table, but you'll find out that the pKa of acetic acid is 4.75 plus the log of 0.100 over 0.100, and that cancels out. So you get pH equals 4.75, and that is before any of the NaOH is added. So then after, when you're solving for the pH change, you're going to be adding 10 milliliters of 0.95 molar NaOH. The first thing you do is you solve for the amount of CH3COOH, and then you're going to subtract this amount from that, and you'll do the same for the anion of the salt, which is a conjugate base. So what you'll do is take what they give you, 100 milliliters of 0.1 molar CH3COOH, so 0.1 liters, and this will be the initial amount of the acid. And then you can you'll do the same exact process with how much weak base you're putting in, strong base you're putting into this solution. Alright, so you get this value, and what you're going to do is subtract 0.01 minus 0.0095 equals 0.0005 moles of CH3COOH left in the solution after you added the strong base. And to find the concentration of that, because you're going to need it when you're using this equation later to solve for the pH, you put it over the total volume. And your volume is not 100 milliliters because now you've added 10 milliliters of NaOH. So you combine that and it's 110 liters, or 110 milliliters, and then you get this for the molarity. The next thing you do is you solve for, you do the same thing with CH3COO minus, except this time you're adding it because they are both bases. So it's the same number because it's the same concentration, so it's going to be 0.01 moles of CH3COO minus, and you're adding this value. And that's of CH3COO minus. And you do the same thing and divide. Oops. And you get 0.177 molarity of CH3COO minus. Okay, the last step you do is you use the same equation from above, and this time for base, instead of doing 0.1, which was the original, you're going to use this number you solve for it, which is 0.177 over the concentration of the acid after the base was added, and so it's 0.0045. And when you solve that, you get pH equals 6.35. and the last thing you do is just do 6.35 minus 4.75, and that'll be the pH change.